Okay, I think it's time to get started. While we're waiting for more folks to join, let me give you a quick introduction to this event tonight and also our speakers. So this is a four event series covering time series in collaboration with InfluxDB. InfluxDB is the company that powers an open source project called InfluxDB, and there are a lot of exciting announcements. The technology is pretty cool. So if you happen to have attended the first session, I think that was very interesting, introducing InfluxDB and Apache ecosystem. And tonight, Anais is going to introduce how to query time series data with SQL. And just so everyone knows, next Monday and the Monday after, we will have topics about tools for time series forecasting, anomaly detection, as well as how to build IoT applications with Python, Flask, and also InfluxDB. So without further ado, let's kick it off. Anais, over to you, and we look forward to this session.
Thank you so much. Hello, everyone. Yeah, so as we mentioned already, I'm just going to be giving a presentation on querying basics with SQL. So if you're already really familiar with SQL, this presentation might be more of a review for you. Someone asked already is that they missed the first session, and I believe that there is a recording on YouTube because I think these are all live stream. So yeah, you can make sure to check that out there. That first session was all about InfluxDB and how it utilizes technology from the Apache ecosystem in our latest version of our storage engine. But yeah, today we're going to just be focusing on how to query with SQL and understanding some of those basics in case you're new to it, and also, specifically some of the tasks that you might want to accomplish with SQL for time series data specifically. So let me share my screen. Excuse me. And just move some things around. Give me a couple seconds. Okay, so yeah, so today we're just going to go over some data querying basics for querying with SQL and InfluxDB Cloud 3.0. So because especially for the SQL implementation that's used for InfluxDB Cloud, it's the same one that is used by the Data Fusion API, and Data Fusion is a framework for transferring large sets of data. And I'll talk more about that in a second, but that's the implementation that we're using. So there's some syntax things that are specific to it. But in this section, we'll basically learn about how to query with SQL, and we'll talk about some SQL introductions and language syntax basics, as well as some basic queries. And we'll talk about grouping with SQL, some aggregators and selectors that exist within SQL. Then we'll give an intro to some SQL subqueries. And then we'll talk about using downsampling tasks and how we would execute downsampling tasks with both SQL and Python, and performing a task to essentially query with SQL, and then maybe share or contain that downsampling task in an AWS Lambda function, for example, or whatever function as a service that you want to use, so that you can perform that on a regular basis. And I'll describe what downsampling is as well. And then if you're not already taking advantage of ChatGPT, highly encourage you to do so. So even if you don't or are not very fluent with SQL, you can use ChatGPT to speak in your native language and craft your SQL queries for you. And in fact, we have a CLI now that allows you to just query InfluxDB in English if you choose that you want to do that instead of querying with SQL. So, and it uses ChatGPT on the back end. So ideally, you come out of this presentation having a better understanding for SQL if you're new to it, but also with the confidence that while you're learning it, you can use these tools to help expedite your learning. And last but not least, we'll talk about some of the learning resources that you can take advantage of to learn more about Influx data, more about InfluxDB, more about SQL, and more about what's coming next. So I want to just kind of, for those of you who didn't attend the last session and are not familiar with what InfluxDB is, I want to bring you up to speed. So Influx data creates InfluxDB and Telegraph. Those are two open source offerings. We also have a cloud version of InfluxDB as well. InfluxDB is a time series platform. So it has at its core the time series database, but there's also a UI that you can use to help you manage your instance. And there's a unified API across the OSS version and the cloud version as well. And you might be asking yourself, okay, well, what is a time series database and why do I need one? Time series database is a database that's optimized to handle any data with a timestamp associated with it. So that can be things like logs, metrics, and traces. Typically, when we think of time series data, we usually are thinking of metrics. We're thinking of like, I'm gathering the weather temperature of a particular city, and I'm gathering that temperature daily or hourly. But yeah, we also have logs, we also have traces, and we also have event data, which is also time series data. Like, if there's a seismic activity, an earthquake, that's not happening regularly. That's not a metric. That's what we would call an event. And so InfluxDB's new storage engine was built to address some of the other concerns associated with time series data. The primary one being that a lot of time series use cases require data that has a really, really broad dimensionality to it, or cardinality, depending on what you want to call it, like a really, really wide one. And in previous iterations of our storage engine, we had moved the entire index onto disk because that's how large the index was to accommodate these incredibly large time series workloads. People were writing, over 800,000 points per second with like a dimensionality of 10,000 points. So, and that still wasn't enough. So, one of the things that we wanted to address was, can we find a way to expand that limit so that we can provide essentially unlimited cardinality? I mean, in reality, we can't actually guarantee unlimited because everything has physical constraints, but for all practical purposes, that was a big goal. And one of the ways that we achieved that was by building InfluxDB's new storage engine on the Apache Apache ecosystem. So it's built on Rust, and Rust is a programming language that's like very performant. It's similar to C++, and it offers really fine-grained memory management. And then Apache Arrow is a framework that's used for defining in-memory columnar data. So that's the in-memory columnar store, essentially. And then Parquet is a column-oriented durable file format. So that's on disk. And then Data Fusion is a query execution framework that's written in Rust, and it uses Apache Arrow as its in-memory format. So all of these tools work together. Data Fusion has a SQL API, but it also has a Pandas API, a Python Pandas API. So in the future too, ideally, you'll be able to query InfluxDB with Pandas as well, which will be, for me, super exciting because I'm a huge Pandas fan. And last but not least, it's also built on Aeroflight and Aeroflight SQL. Aeroflight is a general purpose client framework that simplifies high performance transport of large data sets. So it's built all upon the Apache ecosystem that's very focused on being columnar oriented to achieve really high performance for time series data, so that we can accommodate really high cardinality use cases, but also that we can provide interoperability with a lot of other tools. A lot of business intelligence and visualization tools allow you to import Parquet files. So eventually too, you'll be able to query directly for Parquet files. But you can right now use Aeroflight SQL to query InfluxDB and then really easily convert your data to a Parquet file. So you have that option. Also, querying with SQL provides greater interoperability with other tools. And yeah, so that was another huge emphasis or a huge reason why InfluxDB decided to, for Influx data, we kind of use the names interchangeably, decided to rebuild the storage engine. So with that context in mind, hopefully now we understand like what a time series database is, the fact that time series data is usually requires really high volume and really high throughput and really high dimensionality of your data sets. So you need something that can accommodate that. There's also other small things that make working with time series data challenging. Things like, shifting time, or querying for time, or downsampling your data, which is the process of taking your data that's like raw high precision data and reducing it to a lower precision aggregate. That's a very common thing that's done, and we'll talk about that more in a second. But you want to be able to do that in an efficient way with a time series database. And you also want a way to be able to explore your data in a UI, and making sure that you're working with the same time zone, so that if a colleague is also exploring that data, that you're talking about the same timestamps, because it turns out that like working with time is actually not super intuitive as far as like just managing time and thinking about time when we think about all the different time zones that we're in, and different timestamps. So yeah, just like having a lot of those tools pre-built for you, so that you don't have to use another type of database and add that functionality on top. So with that being said, yeah, hopefully we have the background of what a time series database is, why you need one, and then like what InfluxDB is evolving into now. But for today's lesson, what we'll be doing is we'll be first writing the air sensor sample data set, and we'll write this to InfluxDB Cloud. And it has the following schema. It's got one measurement or table. You can think of them as the same thing. We'll call it air sensors. And it has three fields: carbon monoxide, humidity, and temperature. It also has one tag, or another column, sensor ID, which contains 8 values, TML 0, 100 through 203. So I just wanted to walk us through first and foremost how we would like load this data set if you wanted to execute these same queries. So you could go to influxdata.com and sign up for a free cloud trial. And then what you could do next is to visit this URL and copy and paste the line protocol data. So line protocol is the ingest format for InfluxDB. It's basically the table or measurement name with a comma, and then you have key value pairs for your other columns and column values. And then you have, last but not least, your field, which is like what you want to think of as like the meat of your time series data, like the actual temperature, not the location or, the sensor, something like that. So yeah, so basically you would take that, you'd copy and paste it, and then you would enter it manually. So let's look at what that looks like. So in the UI, if you navigate to the load data page, you can click create button, or create bucket, and bucket's basically a database, and then you can name it and give it a retention policy. So retention policy defines how long you want to retain that data for, because that's another unique thing about time series data, is that unlike like relational data, where oftentimes you want to keep that data forever, time series data, you want a way to automatically expire old data that's not relevant to you, especially if you're collecting data at a really, really high precision. InfluxDB supports nanosecond precision, so it makes sense you don't want to keep that forever. And you want to probably define that and not have to build a mechanism for automatically expiring that data yourself. So then once you've created a bucket, you can click the add data button, hit line protocol, and then select enter manually. First, you're going to select the bucket or database that you want to write your data to. Then you'd copy and paste it here, and then you could say verify whether or not you've written that line protocol data successfully. And if you have, then you'll get this great little confirmation that tells you that you in fact have written data to the database. So excellent, we did it. And so now we can explore our data. And I always recommend, as soon as you write data to your database, to go ahead and explore that data to determine what timestamps to use when you are querying for your data, to like orient yourself with when in time that data has been written. That line protocol link that I shared here, it's cool because it updates, I think hourly or daily, I'm not sure. So the timestamp should be pretty recent. But yeah, in general, you want to know like when was the last point, that you've written data, and you could use like the last function to pull that. But this is what our Data Explorer looks like. It's not meant to replace your visualization tools. It's literally just intended for you to explore your data and have a good idea of what your schema looks like. And then we encourage you to take advantage of InfluxDB's interoperability to use something like Tableau or coming soon Power BI or Superset, Apache Superset or Grafana, and instead visualize your data with one of those tools that are purpose-built for visualization. But that being said, you still probably want to explore your data. So you can use what is called the script builder, and you can select your bucket or database, your measurement or table, however you want to think of them, and then select for all the columns that you want, all the tags and all of the fields. And then you can select run and you can see your data as a table or as a graph. So just kind of as to familiarize ourselves with the UI and the different components of it. On the panel on the left, you can do things like select a new script to create a new script, save the script, open existing scripts, and use the dropdown to build that SQL query like we just did. And it's also important to mention that you must always select the bucket that you want to query data from in order to run a SQL query. If you just write select all from your table, it won't know which bucket you're talking about. So you, at the bare minimum, if you're using the UI, need to do that. And then in the middle panel, which is pink, highlighted in pink there, you can write your own SQL queries. And I should mention too, like write the script builder. If you select all the drop-down options that you want, it'll generate the SQL for you. But in the middle panel, it'll either be generated there or you can write your own. And then you can visualize the output below. And then on the right-hand side in orange, you can customize that visualization. And there's a variety of different visualization types. So the other thing that I would recommend doing as well is to not just use the Query Explorer, but to use the show tables function and the show columns function in measurement to explore your data. And that's what those functions are intended to help you do. So for example, if I run show columns and air sensors, it shows all of the column names as well as their respective data types and the table name or the measurement name that each column comes from, as well as whether or not it's nullable. And I found this especially useful for when I was converting some Parquet files to Hyper files in order to import them into Tableau Desktop. And in that case, it required that I have a quick understanding of how I'm going to convert what where. And so I needed to this summary was really helpful. Excuse me. So, and also in the next presentation, when I talk about tools for machine learning or tools for data analytics and forecasting with time series, I'll also be talking about how you can leverage Tableau. There's also a JDCB connector now that's coming out, so you can be able to query InfluxDB directly, but I'll also talk about how you can convert your files to hyperfiles, which is the format required for Tableau as well, and how I took advantage of that. So if that interests you and you want to learn more about how to integrate Tableau with InfluxDB or other forecasting and anomaly detection tools that I am a fan of that are specific to time series, I encourage you to come to the next talk. But yeah, let's get started actually learning some SQL now. So the key takeaways here is that we're going to query the SQL in InfluxDB Cloud. We can query that in the UI. I encourage you to take advantage of a variety of different docs to learn SQL. Our docs are great. I love our docs team. The select clause is what you're going to use to specify the tag and field columns that you want to retrieve by your query. The from clause is what you're going to use to specify the measurement or tables from which the data values are going to be retrieved. And the where clause specifies criteria that those column values must meet in order to return your query. So real quick, for any of those getting started, I'm just going to share all the documentation links right now in the chat that I am talking about throughout the rest of this presentation. Our docs are really cool, but we have a lot of different versions, OSS and we've migrated some people. So I think the biggest thing to pay attention to is that when you are using the docs, make sure that you have referenced the correct version that you're using and product that you're using in the right-hand side. But all of these docs are with the correct version in mind if you're using InfluxDB Cloud 3.0, so you should be totally fine. But yeah, just in general, I think that's the only thing that could be tricky about our docs. Otherwise, I really appreciate our documentation a lot. So, okay, this is what, SQL would look like. Traditionally, you would say select columns from table where, the columns meet certain conditions or criteria. But in InfluxDB, we say select what is known as tags and fields, which are also just columns, from a measurement, which is just a table where they meet a condition. So typically what I'm trying to say here is that SQL users usually think about tables and measurements, but InfluxDB Cloud, you want, especially if you come from InfluxDB previously, you're gonna be thinking about tags, fields, and measurements instead of tables and columns, but they're the same freaking thing. So columns equals tags and fields and table equals measurements. Don't trip, it's just the, it's just the same thing, just different naming.
I'm sorry, can I hazard a question there real quick?
Yeah, of course.
You can go back to the previous screen.
Yeah.
Yeah, I see it's the same thing, right? Tags and field, but then it seems to be, I don't know, two-dimensional. I see like the replacement seems to be two things. Is that how it is in that particular thing? Does a tag come with each field, or is tag field one thing?
Oh yeah, you can comma separate them, but tags and fields are both columns.
Both columns. So it's possible to have a tag only, because to me it seems when I'm looking at it, it seems as if they go together. That's really my question. So they don't go together. So I can have a tag only and I can have a field only.
Correct. Yes.
Okay.
Yeah. Thank you.
Okay. No problem.
So let's talk about quotes and process order a little bit too. So with SQL, it's really important to recognize that the process order of your query won't match the syntax order. So it's also important to note that double quotes are going to be used for identifiers, things like column names or tags or fields. And single quotes are going to be for string literals. And so the process order is roughly, this is not, exact, it depends on your query, but I generally think of the process order as being select first, as second, from third, where, then in, not in, exists or not exists. And then we have our group bys, our having, our order bys, and our union. And then we have limit at the end. So that's just something to keep in mind when you are writing your SQL queries. So the simplest SQL query that you can write is select star from air sensors, and that will return all the data in our air sensors measurement. Star just indicates that you want to return every column. However, be mindful when you're using this query, because if you've written, millions or billions of points, you might not necessarily really want to be gathering and querying all of your data. In fact, you probably want to use a where clause to limit your data to a particular time range. So let's talk about some basic queries. And some of these key takeaways are pretty much the same thing that we talked about before, so I won't really go into it, but I will say that some of the first 3 links I think I shared is the documentation that I would pay much attention to for this section. So the first question you might ask is, how do I return all the data from the last 10 minutes? And the answer is going to say select star from air sensors where time is greater than now minus the interval of 10 minutes. This is what I mean. This is probably the weirdest thing about this SQL implementation is this, declaration of the interval of that type of being 10 minutes. But it's not really hard to get used to. You just might not have seen that before. And when we do that, this is our result. We have, a column for carbon monoxide, humidity, sensor ID, temperature, and also our timestamp column. And it's in RFC 339 timestamp. So what if we wanted to ask, what is the temperature data from the air sensors measurement for all the sensors? So we could select for a particular column. In this case, we'll just select for temperature from air sensors, and we can, use a different interval if we want, 15 minutes, for example. And so in this way, we've selected for just one column, temperature, which is a field in InfluxDB. And it's really just only a field when you think of it in terms of line protocol when you're ingesting data. But yeah, so we just get our one column back, but it's also kind of meaningless because usually, with time series data, you're usually looking at the timestamp. And then we have another question. What are the first 5 temperature data points from the air sensors measurement for all sensors? So we can say select temperature from air sensors and limit 5. So if we do that, we can see that we only have 5 results returned. And it's also important to note that we can also see and verify that we can not only search our results, which is a really nice feature, but also that we only have 5 rows returned, which verifies that we are in fact limiting our query to those 5 points. And then we might also ask, how do I return all temperature values greater than 72? In this instance, we can say, let's select for our temperature, but let's also select for our time value and our sensor ID so that we have a little bit more context for our data, so it makes a little bit more sense. From air sensors where temperature is simply greater than 72. And when we do that, we can see that, in fact, we are getting temperature values for a variety of different sensors. Right now, we can only see sensor 102 in this screenshot, but we are sure that all of our values are over 72. Another question we might ask is, how do I select the temperature and sensor ID from a specific time range? So in this case, we're going to go ahead and select our sensor ID, our temperature, and our time from air sensors, but we're going to select for a time range where the time is greater than or equal to a particular timestamp, and then we denote that timestamp, and then also where time is less than now, for example. And we can also decide that we only want to select for a specific sensor ID as well. So we can use and to also specify that we want all of our temperature data to come from a single sensor. And so we do that, and we can see and verify that our time is within those bounds, and that in fact our data is all coming from a single sensor ID. So hopefully at this point we have a pretty good understanding of how we can use the where clause to apply conditions to our time series data or to our SQL queries, and also how to select for specific columns or not. So let's talk about using some basic aggregations. So aggregation functions are things like count, average, sum, and then min and max are technically selectors, but I should say basic aggregations and selectors. So what if we have the following question? How do I calculate the min, the max, and the average temperature for sensor 100? What I would do is say select min of the column that I want to get that of the min value of temperature, and then I'm going to rename that column as min temp. Then max of temperature as max temp, and then average temperature as average temp from the same table. I'm going to include some timestamp constraints, and I'm going to apply it to only a single sensor ID. So I can do that, and you can see that I have the average temp, the max temp, and the min temp. So we get all of those values delivered to us there. But it's important to note that the max temp and the min temp, those will happen at a particular time, right? That we can imagine that the min temp of a room we were monitoring the temperature of would be lowest, sometime at night. But average temperature is going to be, an average over across all that time. So there's not actually a timestamp associated with that. So one thing you couldn't do is select for time and min temperature and average temperature. Because there is no timestamp associated with the average temperature. You would have to do that into independent queries and then maybe join them together if it was really critical that you visualize them in one table in your return results. So just worth keeping in mind. So another thing that you can do is you can also find the global min and max without specifying a time range by just simply saying, select min from min temperature from air sensors. And this is a really long time request because in the past, especially if you're familiar with InfluxDB already, there's this language called InfluxQL, which was SQL-like, but you'd always had to specify a time range in your query. You did not have the option to exclude that. Now you have the options to exclude that, and it's much easier to return global values from across all your data. And this is especially true when you have event data and your data is really sparse and you don't even remember when the last time you wrote, some data to InfluxDB was. So you're like, how am I even supposed to, what time ranges do I put? So that problem has been solved, which is another reason why there was this push to use the Apache ecosystem so that we could solve problems like this and do really fast scans across a ton of data. And then you can also use the selector underscore min and the selector underscore max functions, which I'll talk about in a little bit, which are even more performant. So we can use the having clause as well. So now I'll get into some other functions to place conditions on results created by an aggregate operation on groups. So before we aggregated some of our data, we'll talk about aggregating on groups. And it's important to note that the having clause must follow the group by clause and precede any order by clause. So for example, if I asked, how do I return the mean temperature values that are greater than 72? So in this case, we're going to select our average temperature as mean temp. Let's also select our sensor ID as well from the measurement we've been using, the table we've been using. We'll group by sensor ID, right? Because we want to find a average temperature for each sensor ID, and we want to only return the mean temps that were greater than 72. So that's why this having clause requires that a group by, because you need to have more than just one value returned to you, because otherwise it would be, you know, kind of senseless. Like there wouldn't be a lot of point to even looking for that. So it's like within a group set, what has that, right? And you want to return a set in order to like determine what in the set meets that condition. So yeah, so when we do that,
sorry, I have another question if I could. Don't mean to interrupt you. I think I got it conceptually. Could you just hit me with the difference between the where clause and the having clause?
Yeah, sure. They're very similar. You can actually kind of use them interchangeably. So I'll talk about that in a second, and let me go do that. And then if you still don't understand, please ask again and we'll go over it. Does that sound good?
That's perfect. Thank you so much.
Yeah, of course. So yeah, so in this example, we're calculating the average temperature for a variety of sensor IDs, and we're only returning the average temperature or the sensor ID that for the where the average temperature is greater than 72 for each sensor ID. So here's another example. Sorry, I was thinking about in. Let me go back. So yeah, let me explain this better. So essentially, what we're doing here is first this is just the way the having clause operates. So it's always going to operate on something where you've already performed an aggregation, so like an average of something. But it also requires that you perform a group by as well, so that you can first find the average for each individual sensor ID, and then you want to select for the sensor IDs that produce an average temperature where that average temperature is greater than 72. So that's what the having clause does here. So to reiterate, it places conditions on results created by an aggregate operation that has already been executed on groups. So which of the groups, once I perform an aggregation, have this condition, essentially. Does that help answer your question?
Yes, that was perfect. Thank you so much.
Yeah, thank you for asking. Okay, and so then I also wanted to touch a little bit on exist, not exist, in, and not in. I was really just going to focus on in because I think that's the query that I use the most, and it's a good introduction to heading towards subqueries. We're not actually performing a subquery yet, so please ignore this because this is not technically a subquery. To truly have a subquery, you need like multiple select clauses. But essentially, we said if we had the question, what is the max temperatures for sensors 100 through 102, we could do select max temperature where a sensor ID is in TML 100, 101, or 102, and then we could group by sensor ID. And that would be equivalent to saying where sensor ID equals 100, or sensor ID equals 101, or sensor ID equals 102, and then we'd group by sensor ID. And we'll cover some actual subqueries in a second. So I apologize for the typo on the top there. But yeah, just know that those are equivalent, and it's just kind of a shorthand. So when we do that, we can see that we are getting a max temperature for the sensor IDs that we queried for. And then you might have a question right now, potentially, since we have only been working with temperature essentially. How do I graph the temperature and humidity simultaneously? So unfortunately, our UI doesn't allow you to do that. And that's kind of intentional in the sense that the Data Explorer is really just meant to explore your data, not visualize it. We're really trying to push people towards using the interoperability that is available through InfluxDB. So we want you and encourage you to use Grafana, Superset, Tableau in the future, coming soon, Power BI, to visualize your data, or pandas or matplotlib or something like that, Jupyter notebooks, etc. So use like the tools that are intended for that purpose. The only reason why I'm querying stuff in InfluxDB now is just kind of because these queries are pretty simple, and it's an easy way to make sure that we're getting our data back successfully, but we're not really focused on visualizing it, which is why we've been focusing in the table view just to verify that we're returning the data we expect. So now let's talk about grouping with SQL. Essentially, you must use functions like average, min, max, count, etc. if you're going to use a group by. You use group bys to group one or more fields or tag columns together. We talked about this already, but you're required to use a group by before a having clause. And then also we'll use a date bin function to group data by time intervals and perform downsampling. And then you can use the order by function to change the order of the results. So I'd follow the group by documentation for this section. So one question we might have is, what is the mean carbon monoxide value for each sensor? We should already be familiar with this because we've already pretty much done this. We did it with temperature though before, where we're finding the average temperature and we're grouping by sensor. So this should all look totally familiar. But now let's talk about the date bin. So date bin is used to calculate aggregates over time windows. And this is a task that's typically known as downsampling. It's where you're reducing your high resolution data to a lower precision aggregate. And the advantage of doing that is that it's a way of maintaining the general shape of your time series data without retaining that high precision raw data, which can actually prove to be too much noise in the long run when you're just interested in looking at overall trends of your historical time series data. So it's often the case that people want to retain that high resolution data for short periods of time and obtain downsampled data or materialized views of their data over longer historical periods, and you would use the date bin function to do that. So if you had a question like, how do I calculate the average temperature for each sensor over 1 minute intervals? Your answer would be this. You would say select sensor ID, and then you would create these date bins, these little windows where you are going to calculate the average time, the average temperature, excuse me. So you create this date bin and you specify the interval, the time, and the timestamp that you want to start the date bins from. And then we're going to name the results of these date bins, these little bins that we're generating as time, as our time column. And we're going to find the average temperature as mean temp across these date bins. And we're going to find that from the measurement we've been working with this whole time. We're going to apply some timestamp constraints to it as well. And we're going to group by time and sensor ID as well. So we can do that, and we can see that we have the mean temperature for each sensor ID for each little window that we have. And since I selected a short interval, there aren't that many date bins, but another thing to notice is that the result set that we get back, we can see that we have a sensor ID for 100 and then 101 and then 101 and then 102, 103, and then it jumps to 200, but we should have the same amount of results for each sensor ID, and that's because we haven't ordered by anything yet. So if you actually wanted to see all of the results for sensor 100 and then results for a different sensor after, we have to actually perform an order by. So we're going to do that to change the order of our results. And there's two ways that you can use the order by function. You can indicate how you want to order your results by the actual name of the column, like sensor ID, if we wanted to, for example, see of all of the values from our sensor ID returned together, or we could decide, I actually want to order my results by the timestamp. And so we could select the time column instead, or we can numerically say we want to order by the position of things that we selected for. So the first thing we selected for was sensor ID. The second thing we selected for was time. So in this instance, we'll be ordering our result set by time. Yeah, and that's helpful as well. So you could either order by sensor ID or time, or you could order by both simultaneously. It's up to you, but it's just important to be aware of that if you want to, help clean your data a little bit. Sorry, that was a duplicate slide. So let's talk about some aggregators, selectors, and time functions. So we already really familiar with aggregate, with average, min, max, count, and sum, so we don't really need to talk about that much. We talked too about how if you have aggregate functions like average, count, and sum, you can't return a time value for that. So just always keep that in mind because there doesn't exist one. And another thing we'll know or learn about is that there are a bunch of general, statistical, and approximate aggregate functions that are available to you as well. And SQL selector functions are like aggregate functions, but instead of aggregating your data, they select for an individual point, and there is a timestamp associated with them. And we'll talk about some selector functions that are even more performant that return a struct instead of just the columns. And these include things like selector min, selector max, selector first, and selector last, and they return a JSON struct, and we'll talk about how we can access those and use them. And these are some of the documentation titles that I would follow for this section. So these are what general aggregate functions look like. We've talked about these a bunch. We're familiar. And we're familiar with how to use them. But here are some statistical aggregate functions. There are more, but there are things like, correlation, standard deviation, covariance, variance, etc. Different forms of them as well. So you might ask, what's an example of using a statistical aggregate function? So one might be, let's imagine that we want to find the correlation between temperature and humidity. We could do this by using the correlation function and specifying the two columns that we want to find the correlation between. And then the rest of our query would look familiar. We select a time range, and maybe we select for a particular sensor ID, and we get this negative correlation. And if I remembered more about chemical engineering, I would say this makes sense, but I don't actually remember a bunch about the relationship between temperature and humidity before. So I trust that's logical. And we also have approximate aggregate functions. So things like approximate distinct, approximate median, approximate percentile, percentile continuous with weight. And what are all these approximate functions? They're essentially just provide you the same answers as you would regular, functions like distinct and median, etc. Except they use algorithms for increased performance to provide really strong estimates. So technically they're just really strong estimates, but what you can think of them as is just aliases of the other aggregate functions that use less memory. So it's worth being aware of them and worth using them if you need. There's also the selector functions, and they work like aggregate functions, but they return a JSON struct that contains both the value and the timestamp. And this is especially useful if you want to use that value in a subquery. So I'll cover that in a second, but essentially it returns a JSON struct that looks like this, and they're also a little bit more performant as well. So how would I select the min temperature value and return the corresponding timestamp across all sensors for the entire data set using the selector min function? So I would say select selector min from temperature and time, and I would specify the value that I want, which from the JSON struct, which has the title of value. Remember value right there. And then I also want to select the time as well. So basically both values from the JSON struct. And when I do that, you can see that I get a single point. In this case, I was looking at the graph just for fun. And also it's worth noting that if you did want to visualize this in the graph, by default, the graph uses the graph is utilizing graph smoothing. And there's a chance that you might want to not include that if you, for whatever reason, you wanted to graph this, but you probably wouldn't anyways. So that's kind of a, I guess, a helpful tip, but for very select use cases, so I wouldn't really worry about it. But let's talk about subqueries, because this is probably my favorite part. This is where SQL can get really crazy. So essentially, we're going to use subqueries to build more sophisticated queries and do things like perform calculations across tables. And I would use the subqueries documentation to learn more. So the first question I might have is, how do I limit my result first and then order the temperature values? So what you'd have to do is you actually need to change the order that the SQL functions are being operated on your data. So in this case, we have to use a subquery to do that. So I'm going to say select all from first my limited amount of data from the first 5 results. And then I'm going to order by temperature. If I just said select all from air sensors limit 5, order by temperature, I would first be ordering my temperature data and then returning the 5 values once they were already ordered. And we want the opposite. So that's why we're using a subquery. Another thing to note is that whenever you're reading subqueries, make sure to always go from the inside out, kind of like a reverse nesting doll situation, right? You always want to read the very most inner select clause to understand what you're starting with, and then how the SQL is being applied to it from the outside. So we can do that, and we can then verify that we're returning 5 rows. And we'll also notice that our timestamps are all next to each other, which verifies that we first limited our result and then we ordered by temperature, and not the other way around, because otherwise we might see timestamps that are, all over the place. So another question that subqueries solves is finding or performing calculations across tables or across measurements. So if I wanted to ask, what is a correlation between 2 fields across 2 different measurements? In this hypothetical example, this isn't part of the air sensor data set, so we can't actually perform this query, but we can still look at how we would do this. Let's say we wanted to find that correlation between temperature and flow rate. Let's say our second table or measurement that we wrote data into contains flow rate information. We could say select the correlation between temperature and flow rate from, and now we have our innermost query, select first table.temperature, first table.time, first table.sensor ID, and then we're also going to select for our second table.flow rate, our second table.time, and our second table.sensor ID from air sensors as the first table. And we're going to join on air sensors 2. Air sensors 2 is our imaginary new table as second table. We're going to join them on time. So when the first table.time equals the second table.time, and when the first table.sensor ID equals the second table.sensor ID, which just is named that way from the as statement. So yeah, so that's pretty much how we not only perform a more sophisticated subquery, but also how we perform a join. So yay. Oh, look, I lied. It looks like I did write some dummy data to a second table, and that is in fact, we have an example of it here. But again, you can't, unless you write your own dummy table, it's not included in the air sensors data set. So I also wanted to talk about an example of a more sophisticated subquery. So in this example, this is unrelated to the air sensors data set. In this example, though, or it's not unrelated. We're still using sensor ID and carbon monoxide, and but the point of the subquery is basically to find the slope of our temperature and our carbon monoxide. So in order to read this query, we'd start from the very inner query first and then work our way outwards. So we look for the most inner select clause, and I'm going to start down here just because it's like the last thing that we're selecting for, and then I'm going to kind of work backwards as I usually do with SQL. So the first thing that we're doing is we're casting the time values as integer values with this cast function. And then we're going to lag the rows by 1. And then we're going to subtract them from the time that we also cast as an integer that we didn't lag. So essentially what we're doing here is we're finding the difference between an n+1 row minus an n row in terms of position, so that we can find the interval between two subsequent records. And we're going to save that value as time. So eventually we're finding the change in X, right? And then we're going to also apply that logic to temperature. Of course, we don't have to cast our value as an integer in order to subtract it because it's already a float, so we can already perform math across it. So we only need to lag. And we make sure to order by time everywhere too, just to make sure that we are in fact finding these delta changes for subsequent records and not stuff that's out of order. And so we do the same thing for temperature and for carbon monoxide so that we can find the change in carbon monoxide and the change in temperature and the change in time. And we title those, CO underscore delta, temperature underscore delta, and delta underscore T respectively. And then from there, we can actually look to the outside of the outer part of our subquery and select for time, which we're selecting there. And then we also want to take our CO, which are delta underscore V, which is essentially our change in Y, over our change in X, which is our delta T, multiply by 1 billion so that we can convert our nanosecond to seconds, so that we have something that is a little bit more intuitive to read. And then we name that CO rate. And we do the same thing for our temperature data as well. So this is an example of a sophisticated subquery that could be used to find the slope of your data. And so that being said, now that we've kind of like wrapped up the SQL portion of this, I wanted to really quickly talk about downsampling. I've already talked about it. It's a specific type of data processing job used to transform high precision data into lower precision aggregates on a user-defined schedule. And it allows you to manage your time series lifecycle, reduce your overall disk usage as you collect data over time, especially important if you're running an OSS version, and eliminate the noise of high precision historical data. So this is how we could do it with Flight SQL. So essentially, you're gonna include whatever your SQL query is, usually using datebin, but you could also downsample in Python or Pandas itself. Then you're going to instantiate the Flight client. You're going to pass that SQL into the client to execute it. And then you can convert those results to pandas, for example, and then work with them from there. So that's essentially all I would do to downsample with InfluxDB Cloud. These were pretty much the only requirements: is Flight SQL, the InfluxDB client, if you want to write that data back to InfluxDB, and pandas. And so you would just need to gather some authentication credentials. You need to instantiate your Flight SQL client like I just showed. So yeah, essentially we import our dependencies, gather authentication credentials, instantiate our Flight SQL client with those credentials and the bucket name that we want to be querying our data from. And then we execute a query against Flight SQL. So in this case, we're using that datebin function to actually go ahead and downsample our data with SQL. And then we create a reader to consume the results. And then we read all the data into a PyArrow table that we could then convert into pandas if you wanted to. Could work with it that way, or we already have our PyArrow table. It's up to you how you want to work with it. I like to convert it to pandas though, especially because if I'm writing that data back to InfluxDB, then I'd use the InfluxDB client to do so. And I'd use the write API method and pass in a data frame as the record and automatically write my entire data frame back into InfluxDB. So yeah, and then I would use something like AWS Lambda or another function as a service to, or even a cron job, it's up to you to perform this downsampling regularly. Yeah, last but not least, I'm guessing a lot of you are pretty familiar with how powerful ChatGPT is. I highly recommend you take advantage of it, especially if you're new to SQL and you're wanting to learn. And then the only real learning resources to wrap up is InfluxDB University. We offer free courses on all things InfluxDB and Telegraph. Telegraph is our collection agent. So you also earn virtual badges with it, and it's just a great resource. Yeah, you get a cool badge that you get to put on your LinkedIn. Here's some more resources. If you have any questions about any of this or what to look for next, I encourage you to reach out on the forums. We also have a really active Slack. Influx data or github.com/influx community is a repo that the developer advocates like myself maintain, and it contains a bunch of examples for how to use InfluxDB. We have some cool demos on building IoT applications, on monitoring an application with open telemetry standards in Jaeger. In Grafana, we have some computer vision solutions that we've done, like examples, all sorts of things. So just go check it out there. We have our blogs, we have our docs, and I mentioned InfluxDB University already. So thank you so much, everybody, for your time. And if anyone has any questions, please let me know.
Yeah, hi. Can you hear me?
Hello. Yeah.
Yeah, so I wanted to go to that sophisticated subquery. And so what's the difference between, like when you are casting the time stamp into begin, how does it convert? And is casting same as using the double colon? So for example, when we lag and cast time as begin, so in this case, time is a timestamp, right?
Yes.
And so in the begin, it would be a gibberish long number, I believe.
Correct. You're right.
Okay. And so this is one syntax, and another syntax which I saw in one of your slide was using double colons after the variable.
Yeah, so I think that's just declaring the type, and this is actually converting the type. Yeah, so the previous is just like a strange, just like a syntax requirement for this implementation that's used by Data Fusion.
I see. Okay. And over is also interesting, which I saw here. So like first we order by time, and then we cast over it, and then we subtract it. Okay. Thank you so much. Yeah.
Yeah, thank you for asking. Well, I thank you, everyone. I think that pretty much wraps it up.
All right, cool. Thank you very much, Anais, for another great talk. And we very much look forward to the next one. Just so everyone knows that we still have 2 more events. One is next Monday. We'll be covering time series, the tools for time series forecasting and anomaly detection. So if you're in the ML data science space, I think this is going to be a very interesting topic. And then the Monday after next week, we'll be covering building an IoT application with Python, Flask, and InfluxDB. So look forward to the next session. Thank you very much for the.
Thank you.
And thanks, everyone. Bye.